No clue what it is. Okay, welcome to the sixth lecture on multibody dynamics. Two things. I hate this room. You probably too, because you're so cramped together, and how do you make notes and so on. So it's suboptimal, but this was the best I could get. I want to stay in the faculty, and I don't want to go to another building. The other thing is, I noticed that there was a large queue before the door, before the start. I don't know if it's allowed, but please pick up the key if the room is still closed. I have no problem with that. Pick up the key and all that stuff, and then it's open and everybody can find a seat. You have to sign off, of course, but that's not a problem. Okay, before we start, this is the second half of the match, right? Will somebody please serve as porter? Thank you. So this is the second half of the match, and well, I have the feeling that we had some transients with a peer grade system. I have the feeling that we're now kind of settling to some steady state behavior. But I'm curious, of course, about your reactions to the whole thing. So are there any pressing questions or comments you want to give? Then I would like to give you the floor now, before we start. Yes?
I uploaded for the previous assignment my thing, but later when I checked, the upload only had the fourth and fifth tone. The first three were totally blank. And I checked my file again, and that did have text in it.
It is a known problem that the showing of an uploaded PDF sometimes has problems in peer grade. We put an announcement already some time back on the announcement board that it's always good if you do grading to download the PDF.
No, like the thing I uploaded, I checked my submission, and then
by downloading
blank pages.
Okay.
Even though the file I uploaded did not have blank.
It's a technicality. Please discuss it with the TAs.
Sure.
Huh? Any other? Yeah.
Yeah, for the last one, for submission 5, I uploaded it, I did peer grading, and I get a score. But when I checked later, the score was changed.
Yeah, a little bit.
First it was 90, then it was 84, and then another time it was 95 again. So I don't know how these scores are determined anymore.
Yeah. Well, it's very simple. I don't know either.
Yeah, but that's quite strange.
No. So that's more the joke answer. So the serious answer is like this. The major part of your feedback grade, we have two grades. It's your submission grade, that's the work you did, and the feedback grade, the work you did on the feedback. How the feedback grade is determined is also dependent on the reactions on the feedback of the guys you reviewed. And that takes some time for people to react. And if people... Can I finish?
Yeah, but the reaction...
Can I finish?
...was not there yet. So it was already changed in the intermediate.
Can I finish my... Yeah, okay. So it depends on the reactions, but it also depends on how everybody else graded and all the reactions of the others. So it's really like this, because it is a community thing. It is for the feedback we can only grade you in comparison to what others are doing. And if you're really interested, send me an email and I'll send you the whole scheme of how your feedback grade is finally determined. Yeah. So it is very complex. And it changes a little bit in time, but not big changes. Okay? More questions? If there are no more questions, then let's kick off with... how do we usually start? Kahoot, hè? No, let's do this. Oh, here we are. And number 6. Yeah. Classic. Okay, yeah, let's start. Okay, where did I go wrong? Is my first impression when I look at this grade. But so why did everybody choose the green answer? Or most of you choose the green answer. Newtonian mechanics and D'Alembert forces. Yes, those two are ingredients, but one very important ingredient is missing in that list, and that is virtual power or sort of variational principles. So that answer is incorrect. And Langsdorff's variational principles is of course not sufficient enough. And if you read the chapter on the TMT method, in the introduction it's clearly stated that it's based on Lagrange's book, Analytical Mechanics. Okay. Is 485 in the room? No. Okay. This is a little bit more difficult. So most of the problems are just from the first quarter, just like a recap of all the different topics. Just take a piece of paper, scribble away, discuss with your neighbors. He's probably wrong and you are right, and vice versa. Maybe you want to use the principle of virtual power to derive it, or virtual work. So it's almost a tie, 50-50, which is not so good, I think. 50% wrong, 50% right. So what is the problem? Well, if you determine what the velocity is of this force in terms of the velocity of this angle, alpha dot, then you can determine what the power is this force, virtual power, makes, and then you divide it actually by the angle, and then of course the other reasoning is, well, it should be some torque. And what is the torque? Well, this is the force, and the distance is L cosine alpha, right? So, okay, 2 more ways to get there. Arivan, good. Keep up the good work. This is also a famous problem from the first quarter. But please read all the answers closely. Yeah, very good. On purpose, this time I show two correct answers, right? Because I never stated that there's only one correct answer. Well, there's nothing much. These are almost equivalent. Mass matrix has a zero eigenvalue and a zero determinant. Okie dokie. Yeah, this is about impacts. And you have 2 minutes, so really take the time to do the calculation. Maybe you should have discussed more among each other. I think I should take some room for explanation. So we want to know by which the velocity of this point hits the ground, right? Well, this is a fixed point, and if this is the angle alpha, or A, and this is a constant length, then the velocity is perpendicular to this one in this direction, right, of this point. But we want to know the velocity of this point. Well, if we want to know the velocity of this point, we have to know the velocity of this point, we already know that, plus the relative velocity of this point with respect to this one. Meaning, again, that's the angular speed times the distance. Since it's minus b here, the velocity is in that direction, right? Now, for the impact, we need only the vertical component. So the total velocity of this one is this one plus this one, and with the vertical component is the sine of the angle. Well, when it hits the ground, both angles are identical, of course. It's a something triangle. So we take L times alpha dot plus L times beta dot, and then sine alpha for the projection. Okay. Next question. Last one. This is about today's topic. Yeah, okay, very good. So let's look at the results. Ta, ta, ta. Okay. Please give me feedback. You've got feedback. I want feedback. You feedback, I feedback. Okie dokie. Feeling's getting a bit better. Okay, thank you. Let's go to today's topic, right? Let's kill this one. This one. This is still running, that's good. Yeah, so today's topic, numerical integration of ordinary differential equations. Until now, so the whole first quarter, so the first quarter we spent on deriving the equations of motion, right? Either in two forms. Either we had the DAE form, where we had this big mass matrix, then we had some matrix C transpose, and then here a matrix C and a big zeros and x double dot Lagrange multipliers, these were vectors, and then right hand side forces and some magical terms, C2 x dot, something like that. Or we had a simple form where we used like a TMT method or a Lagrange equations of motion approach, various ways eventually to get it into independent generalized coordinates. And basically it came down to m bar is q double dot equals, and then on the right side we had a vector q dot. So two ways to get the equation of motion. Now that's all very nice, but we are not interested in that. We are totally not interested in that. We want to know the motion. Want to know the motion and maybe also forces. So how do we do that? Well, how do we know the motion? So we want to know either x of t or q of t, because given q of t we can then solve what x of t is. But we didn't solve for that. The only thing we solved for was the following problem. It was given at some t is t0. We knew the positions. Let's go back. Let's do that. We know the positions. Some q is q0, and we know the speeds. And then from that we could solve, and we have, of course, a differential equation. Q double dot is the right hand side forces. And then from that we could solve what the accelerations are. So that's the only thing we know. Whereas we like to know what is q of t. And that equation of motion doesn't give us an answer. So what do? Integrate, analytically? Why not? You spent part of your high school, great deal of the first year math class on how to solve all these differential equations. And now you get a differential equation and I say, do you want to solve it analytically? You say, no. Why not? Because you have a computer, yeah. Other reasons? How do you solve actually a differential equation? How do you do that? Any ideas? Okay, let's step back. How do you determine a derivative? Because in finding the integral of a function or doing the derivative, those are the two actions which sort of counterbalance each other. So the derivative, how do we do that? X dot at point t was the limit of h going to 0 of xt plus h minus xt divided by h. That is the definition, right? So this is just an algebraic operation. You can put in anything, calculate what this whole thing is, take the limit case, and then you get an answer. Straightforward calculus, algebra. There's no tricks needed. You can do x squared, and if you do, you want to suppose x is t squared, and then what is x dot is the question. Well, you just fill it in. And you say t plus h squared minus t squared divided by h. Oh yeah, and then h has to go to 0, the limit case. And then when you expand that, you see automatically the first thing disappears. You see I have to take the limit case of h going to 0 of, what is the answer then? T squared disappears, so we get 2th plus h squared divided by h, and it's very simple, the answer is 2t. I mean, it's algebra, and you can put in anything. Okay, now we go back. Now I write something like this. X dot is t cosine t plus e to the power t. How do I find x? Of t, of course. Is there an algebraic way to do that? Is there an algorithm? Can I use calculus? Can I use the inverse maybe of this definition?
You can do it through partial differentiate, partial differentiate.
Oh, it's okay. Any ideas? No idea? How do you do it? I mean, you spent one whole year here at university doing it. How do you do it? How did you do it? Nobody? Well, the answer is table lookup. So you have a book where you have f, and then you have the integral, capital F, and then you have a big table, and then it says, well, x squared. I have x, then the primitive is 1/2 x squared. Well, maybe there's also a general formula for x to the power. And then, if you have sine, then sine x, then, oh yeah, it's cosine x, right? And then the table goes on and on and on. It's table lookup. There is no way, there is no calculus, no algorithm whatsoever to find these primitives of functions. Or in other words, this operation, differentiation, is a one-way street. The moment you go in, you can never get out. You're lost. In the end, you get a derivative, and if you know, where did I come from? No idea. It's lost. You can look it up in a book, but there's no algorithm to go back. You cannot put the car in reverse and go backwards. No way. Your car only moves in one direction. So that is a bit disappointing, because if you then have analytical expressions for differential equations, it's hopeless to solve them in this way. And to get a gist or an idea that this is really true, probably some of you have tried in software like Mathematica or MATLAB Symbolic to find the solution of a differential equation. Can I see hands for those who ever tried that? Solve, yeah. And did it work? sometimes if the function was x to the power n maybe, and if there were some cosines and sines, but the moment you write a complex expression, you hear in your computer and nothing happens for you. You feel nothing happens. So as a mad guy, it's looking up all kind of solutions and comparing it and doing all kind of combinatory tricks, but he cannot find it, of course. Okay, so we're stuck with it. So please never forget, differentiation is very simple. That is an algorithm. Finding the integral of functions is just table lookup, and it's undoable work. So what do? We instead of using analytical integration, we use numerical integration, the topic of the day. So how does that go? So how do we do numerical integration? How does that work? Well, we start with some solution. So we have this Q0, and then we also know what the speed is, and we know what Q dot 0 is, and then we times the step size. That gives us our new value. And it's a very intuitive way. It's like, okay, I'm now in Delft, and I have to be in Rotterdam, and I know that my speed is 20 kilometers per hour, right? And yeah. Well, if I cycle for half an hour and I start at 0, then I'm already at 10 kilometers. Oh, I'm still not in Rotterdam. Right? So that is the intuitive way by which you do numerical integration. And of course, we have our state is not only the position but also the speed. So if we want to know the speed, then we take the old speed plus the step size times the acceleration. That's why we need to know what the acceleration is. And that gives us then at t is t1 our value of q1 and q dot 1. And then the whole thing repeats. We go up here and we put it in and we take a next step, and then you evolve in that. And you can compare it to making a plot of a function. Let's say it's one-dimensional. You know some value at t0. For instance, at this point you know a value, and you also know the speed. Well, the speed is, of course, by definition, the slope of the thing. And then what you do is, you say the slope doesn't change so much, so after a step size h, I'm probably here. And then you calculate again what the slope is, and then maybe the slope becomes like this. And then you do again a step size h, and then you end up here. And then you do the slope, and maybe the slope is like this, and etc. So you continue, you march on, and you find finally the function x of t. In a discrete way, of course. You find these points. Not a nice smooth function. If you want to have a smooth function, what do? Smaller step size, more points, fit the function locally to smooth it. There are various ways to do that. Okay, what is the origin actually of this one? So the origin or the basis of this x is x plus h times x dot. Well, let's look again at the definition. So if we have x dot definition at t, how is it defined? Limit h to 0, xt plus h minus xt divided by h. Well, if you just wiggle a little bit in this formula, I can say, then qt plus h equals, qt plus h times q dot t. Right? Well, almost right. There's one thing which I threw over the wall, and that is limit. So if you do this, then be sure that you use small values of h, because this formula is, of course, for h goes to 0, and if I take large steps, that probably is a very stupid way to do it. Well, this is an intuitive way to say where does it come from, and it's the same math you do, like I'm in Delft, I want to be in Rotterdam, I go 20 kilometers per hour. That math is actually this math you are doing in your head. But actually the origin is of course in Taylor expansion. Taylor expansion of a function. And in general, a Taylor expansion is written like fx plus h is fx plus the first derivative times h plus, we usually turn it around. Where was I? Come on, go back. We usually start with h times f prime plus h squared divided by 2 f double prime plus etc. And then you get h to the power n divided by n factorial f, and then the nth derivative. And on purpose I write it with a capital to say it's not a power, but it's the derivative. Okay, but if we then look at this formula, we only do this first part, right? We don't do this. Why don't we take higher order derivatives? We could. I mean, we could say, well, x1 is x0 plus h times x dot 0 plus, since we have the acceleration, h squared over 2 x double dot 0. We could do that. Why not? And then for the speeds, we say q dot at 0 plus h q double dot. Yeah, we don't have the third derivative. We could have. No problem. How do we get the third derivative? Suppose you want to do this. Suppose you want to say, let's put it in plus h squared, just to be, well, symmetric, or to treat them in the same way. How do I get this thing? Any ideas? How do I start the lecture? Integration is table lookup. Differentiation is just calculus. So you just take your equations of motion, which were like m q double dot is q, right? And you just differentiate them. So you say, oh, okay, m dot q double dot plus m q triple dot. Oh, that's not a nice triple, right? Ooh, go back. Ooh. Triple dot. 1, 2, 3 equals q dot. I mean, it's work, and of course you don't want to do much work. You want to sit in the sun and so on. But for now, it's work, but it's doable. Yeah, you can solve it from this. You can say apparently q triple dot is m minus 1 times this q dot minus m dot q double dot. Okay, but not, we're not going to do that for now. It's just to show that it is doable. Does anybody recognize this from his high school days? Yeah. What do you recognize? Like S equals S0 plus V times T plus 1/2 AT squared, right? So that was the formula you learned when they said if there's a constant acceleration, what is then the distance traveled? So for constant acceleration. Meaning that higher order terms are not present, because the derivative of the acceleration is by definition 0 if the acceleration is constant. So this was a perfect formula for constant acceleration problems. Now, the things we are doing in multibody dynamics are usually not constant acceleration, so that differs a little. Why is this better with the term than without? So if we cancel this or we add it, what happens? How is it better? More accurate, probably, right. For the same step size, it's more accurate. On the other hand, if you take a smaller step size, you're probably also more accurate. And that's the thing we're going to investigate today. So what happens when you change the step size, and does it become more accurate, or what happens if you change the method? Does it become more accurate, yes or no? Okay, an ODE in general is usually, yeah, what did I write here? Usually, yeah, an ODE problem is usually written as, so if you take any textbook, math textbook, and you look at ODEs, then they usually say, oh, y prime is a sum function of x and y. And that's usually the way how they pose that problem. And then with some initial condition that y at x0 is y0. So that is their initial value problem. But we have, of course, our derivative is time, so we have y dot is some function of time and y. And actually we don't have that. We have it more complex. We have something like no, we have m q double dot is, yeah, forces which are in itself a function of time, position and velocity. So it's very nice. This in the textbook we can translate to this, but this is not what we have. We have the second order system. So what to do? And usually the initial conditions are here that q at t0 is q0 and that q dot at t0 is q dot 0. So what to do? Any ideas? Can we rewrite the second order equation into a first order equation? Yeah. Very simple. If we now substitute, for instance, q dot is p, that's a nice set of differential equations. Nice, linear, simple. But now we use this extra variable and we substitute that in the equation and we get m times p dot is q of t, q, and p. And so now we have enlarged our problem and we have introduced a new variable. So we've made a vector actually q and p. And then we want to know what is y dot. Well, that is actually q dot and p dot. And what are they? Well, q dot is very simple. Q dot is p in itself, the variable. Very simple differential equation. And p dot, well, that's m minus 1 times the q of t, q, and p. So by introducing a new set of variables, we can make from n second order differential equations. We can go to 2n first order differential equations. So we enlarge our number of variables and of course also our number of differential equations. However, it's very simple, the one we introduce. And now we can cast it in the standard form. So all the methods we are then look up in the textbooks, we can then use for our second order systems. Okay, and in the book there's an example on, for instance, if you have a mass spring system, mass spring damper, how do you cast that to a first order? Okay, the thing we did until now, so the numerical integration, so the numerical integration step, which we did now, and I'm now writing it in the standard format. In plus 1 is in plus h times the function at tn yn. This is the general way how we talk in differential equations, land about differential equations. And this is the differential equation, this is y dot, and the index, the sub-index means t plus 1 or t plus h or next step. This method, this very simple scheme, is known as, how do we call this? As a which name goes by this? Lagrange? Euler? Heun, no. This is Euler. This is an Euler step. So that's the most simplest one. And why is it called Euler step? Well, probably because Euler was one of the first who used this technique to solve his differential equations. Because he also was one of the first who came up with these rigid body differential equations. Now, there are more accurate methods, somewhat more refined method. We already saw with taking the higher derivative, but that is then usually written like this: y star n plus 1 is yn plus h times f at tn and yn. And now instead of saying, okay, we're done, then you do it again. You say, okay, I'm going to recalculate it, but now I'm going to take the derivative at the beginning and the derivative which is estimated at the end point, tn plus 1, y prime n plus 1. So I take sort of an average of the two derivatives. And then this is then the final answer. The name which goes by this is, we call this Hoynes method. And there is a, well, if you make a graph of this, it goes like this. At some point where we have here Tn, and we have here this value of Yn, then we know this derivative. So this is this f Tn Yn. And then we estimate here this point, so y star, just with this h, and this is Tn plus 1, h. And then in this point again, we just calculate the derivative, and for Pete's sake, let's say it's less. So this is now the derivative at Tn plus 1, y star n plus 1. And then what do? We take the average of these two, and then the endpoint is somewhere in between. So probably this will then finally be our y n plus 1. Sorry. Because we take sort of the curvature, the change in the slope into account. And if you think curvature, then you also think second derivative. So this is sort of a way to include the second derivative without calculating it. That's sort of smart. Instead of doing a whole calculation on the differential equation, we say, no, we take an estimate and then we recalculate. Yeah. Let's do a coffee break.